Carlos is the ESO Apex project scientist, and he will tell us more about the last chance to observe with Apex. So Carlos, maybe you can share your screen.
Let it here, and then it comes here. So should be able to see my screen now.
Yeah.
Yeah. So yeah, welcome. So yeah, it's the last chance. So on Apex, so I'm going to give you a bit of an overview of what Apex is and what science you can do with it, and some hints what you can do, but also a bit of last updates on the available instrumentation, so that you know what is really the best we can use right now. So first, some science of what Apex does, because I presume a number of you are mostly optical astronomers and users of the VLT, but Apex is, like ALMA, is an instrument, is a telescope that can give you lots of complementarity science, and that has been one of the goals of Apex, to really to draw the ESO community also a bit to submillimeter science. And now, of course, I will not talk today about ALMA, but of course ALMA is available too. But I'll give some specifics about what Apex has been doing specifically on science results. So starting with the galactic science, so there's here on the top left, you can see some, a map of CO, actually 3 to 2, I still have a typo here. So it's the carbon monoxide gas that has been traced with a SuperCam instrument, which is not available now, but it gives you an idea that you can trace very wide areas of molecular gas in the Orion star-forming region. And in the bottom, you see a result from Alvaro, who's actually on this call, I think, where he's looked at a very dense gas. So the CO goes more for the diffuse gas, but what Alvaro has been looking at is like the N2H plus 7 to 6 transition with the CPS 660 receiver, which is a high frequency receiver that allows you to trace the very dense gas, which is, of course, where the stars are forming from. It's really from the densest gas. So you can get the gas that you really don't see in the optical, that is completely obscured, that you can easily detect with Apex, also in wide-scale mapping, because the spatial resolution of Apex is not necessarily great. It's not ALMA, of course. ALMA gets you to many subarc seconds to almost to 50 milliarc seconds, but Apex gets you a wider field of view. That's the big difference between Apex and ALMA, I would say. And on the right, you can see actually the dust continuum emission. So this is really emission emitted from dust done with the Artemis camera at 350 and 450 microns. So you can really see these very long filaments of an even larger scale than what is in the bottom. So you really see, again, the dust emission that's from where the stars are forming from. Then moving out a bit further away, so first still in the Milky Way, there's been a paper from Di Teodoro et al. And CO2 to 1 in the top left, where he has found outflowing gas, so bullets, as he almost called it, being ejected from the Milky Way. So that has also been quite well done with Apex, because we can easily detect large cubes, make big cubes, and these were H1 selected, but I think it was with Arecibo at this time, but also with other SKA precursor telescopes, and they did the follow-up in molecular gas with Apex and found these outflowing gas. So that's again something very complementary. If you don't know exactly where to look, it is a good thing to start with Apex and then do the fine-tuned observations with ALMA. In the bottom left, I don't think I need to introduce this image too much, but Apex has also been participating in the Event Horizon telescopes, and will also be doing this actually next week. Again, there will be another session starting on the Event Horizon telescope where Apex is also participating. And then going to real extragalactic science on the right, you can see 2 examples of a carbon CO120, a carbon 1, but also carbon 2 on the top. Where really with the high frequency receivers and receivers that ALMA will have sometimes even going beyond the frequency range of the ALMA receivers, you can detect in the top the C2 grass, and in the bottom the other tracers. And this is of course a bit harder. And I would say Apex was a bit more of a doing pilot surveys, so for that this gas can be detected. But once you can detect them with Apex, you can actually map them with ALMA. So that is a bit the idea, that if you can spend 5 to 10 hours of observing time with Apex, and with the same amount of observing time with ALMA, you can then do detailed observations. That was a bit of an overview of what kind of science Apex is doing. It's of course much broader than this, but just a few overview highlights. So then, how is Apex operating? So it's the telescope is actually a prototype of the ALMA antenna. So it was, that's why also was Apex was there on the same site as ALMA, a few kilometers away, and if ALMA is in the extended configuration, Apex is actually in the middle of ALMA almost. So it has been adapted a bit to use as a standalone telescope. So basically some Nesmith cabins have been added and an instrument container. So it has lots of instruments. It's also an instrument platform, but that is of course different kind of used. But that it has actually been very good to showcase new technologies that can then be implemented on ALMA, and it will continue to do so in the coming years. So Apex is a collaboration between different partners, of which ESO is one of them. So the Max Planck in Bonn, ESO and Sweden are 3 partners, and Chile also gets the guaranteed 10% of observing time. And all of these proposals get, unlike ALMA, where this is one proposal allocation committee, time allocation committee that does this, on Apex it's been all separate. And so Apex has been running since period 77 in 2005. So there's been quite a number of years that ESO has been offering it. And the ESO oversubscription has been the highest of most of the partners most of the time. And it's fluctuating a bit. So we've had peak oversubscriptions of more than 5 to 1, even when La Boca came online, there was a very new bolometer array. But sometimes it's been a bit lower, down to 2 to 1. So it's on average, I would say it's around 2.5 to 3 to 1. So it's still oversubscribed, but not as high as the VLT or ALMA, of course. So it's easier to obtain Apex time than ALMA time. That's if users ever wonder. So the original plan was for Apex to run till 2012, and because there was quite some interest and new instrumentations coming, this agreement has been extended actually 3 times already. But of course, at some point you have to make investments, and the last extension from 2018 to 2022, then it was clear that we had to make upgrades to the telescope and the whole secondary. So basically, what you see in the picture here, the panels and the secondary support structure and the secondary has all been replaced, because that really we would not have been observing with Apex if we hadn't done this 4 or 5 years ago. So now the ESO agreement will end. So the current agreement ends at the end of this year. So this is why we're getting the last call for proposals this time. And so there's no more extension. So ESO is participating in a different way. So Apex becomes a hosted telescope from next year onwards, but it will be cost neutral to ESO. And there will no longer be ESO observing time. So that basically means that ESO will still, the Apex telescope will formally still be on ESO ground with a few ESO people working on it, but most of the staff will already move away from ESO contracts anyway. So this is the last call for proposals. So the deadline is, as you probably have already seen, is the 24th of March. And of course, for DDT proposals, you can still submit them, but that will not be till the end of period 110. That will be till December, because the last ESO observing time is in December of 2022. And I would also recommend not to wait too long, because the longer you wait, the less chance you get to get DDT proposals observed. So definitely don't wait too long. If you miss this deadline and have a small observation that you think is still relevant for DDT, you better be quick with it. So in the future, the Max Planck time will remain open to those of you who are attached to German institutes would still be able to apply, and also those of you in Chile would be able to apply. If you're not, then you will have to collaborate with scientists in those regions. So that's one way of getting a bit more of observing time, is collaborating with those who continue with APEX. But it will not be offered on ESO time anymore. Also, the data that will be observed beyond next year will no longer be stored in the ESO archive. So you will also not be able to use the archive for new data after ESO has been discontinued to offer APEX. So quickly on the instruments. So the main facility instruments are NFlash and SEPIA. So NFlash is shown in the top right. So it's actually an instrument that can observe two bands simultaneously. So two frequency bands from 196 to 281, corresponding mostly to ALMA band 6, and from 378 to 507, so mostly corresponding to ALMA band 8. But the new thing is that now finally the dichroic, which you can see is this little orange round-shaped on this pedal, which is a dichroic that will actually split the light going into both of them simultaneously. That is now finally available. There was a bit of a delay also due to the pandemic, unfortunately, that simultaneous option was not available. Now in period 110 it is available. So that is one thing new, that for those of you who have used APEX already, now you can take that into account, that you will get, basically you will get the 230 for free when you do 460, because you need good weather for this. And here's one of the hints already. If you're trying to use APEX, think of proposals that can use bad weather conditions. So the 230 NFlash 230 receiver can be used with easily up to 5 millimeters of, well, 5 is pushing it maybe, but 4 millimeters is not an issue, and going up to 5 millimeters is definitely an option. And as that time is always less oversubscribed, we allow proposals, even regular proposals, to go up to 199 hours. So you can, and people have done that in the past, submit larger proposals, larger regular proposals for this instrument, but only if you're asking for conditions that are not so good weather. So it's really, it's a way to fill our queue if the weather is not so good. So that's why we really allow larger proposals, twice as large as regular ones. Then the SEPIA receiver, which is a property in the SEPIA color in the bottom right picture, actually has 3 bands. Again, the first one is exactly a copy of, and those 3 are almost direct copies of the ALMA receivers, although the first one is a complete copy. So the band 5 receiver of ALMA is the SEPIA 180 receiver for APEX. Then the second receiver is a copy of APEX, but of ALMA band 7, but it's not directly a copy. It's actually a copy of what the future, one of the potential future ALMA receivers will do, because it has twice the bandwidth of the current ALMA receiver. So it has 8 gigahertz of bandwidth, while the current ALMA receivers have only 4 gigahertz of bandwidth. So that's one of the nice differences. Then the last receiver is SEPIA 660 that covers the ALMA band 9 band, but it goes well beyond it. It adds almost 20 gigahertz on each side, which can be very interesting for some local lines which are not observable with the ALMA bands, but also for redshifted lines. If you just shift right out of the ALMA bands, then you can actually use this receiver to observe them with APEX instead. And I should say that both NFlash and SEPIA are connected to the backends that records the 2 sidebands simultaneously. So you either have 4 or 8 gigahertz bandwidth. So 4 gigahertz is for this band, ALMA band 5, and the ALMA band 8. So that's basically those 2 have 4 gigahertz, but most of the other ones are actually a larger a new generation where you get twice that bandwidth. And you get very high spectral resolutions up to 60 kilohertz. So it's also very important if you want to do very high spectral resolution observations, then APEX is very good at this. And you get it over always over the full bandwidth if you need it, of course. Then a new receiver that has been offered since period 109 is LASMA. And this is a PI instrument from the Max Planck in Bonn, that they allow us to use it in collaboration with them. But you can request ISO observing time on this LASMA instrument. So it works in basically, again, like ALMA band 7, so the 345 gigahertz band. So it actually goes a bit wider band here, 268 to 375. So the nice thing of this is now that also after a recent upgrade, you can go up to 8 gigahertz per sideband. So again, you have the broader sideband, and it allows you to observe the two isotope logs of CO32, the 13 and 12 CO simultaneously. So if you want to map regions, star-forming regions or gaseous regions, you can actually use this instrument to map it simultaneously. And this is actually quite a sensitive instrument, so you can go to medium faint or actually quite faint regions, because your mapping speed is of course 7 times faster with 7 pixels available. So if you want to use this instrument still for the period 110, you should very soon contact my colleague Friedrich Furowski in Bonn, because you need to set up a collaboration and check that this is not something that they are already doing. So it is a collaboration, but it's not supposed to be a competition with them. So I would say you really contact him today or early next week, so that there is enough time to make sure that your proposal does not compete with any of the ongoing plans that they have. Then bolometers. So bolometer instruments, they can map continuum emission. So we have 2 of those instruments installed in the gas screening cabin of Apex. So on the left there is Artemis, on the right Concerto. So Artemis has been available for quite a while already. So it offers simultaneous imaging of at the 350 and 450 micron bands. It has a field of view of 2 times 4 arc minutes. So it's a medium large field of view. And it's the sensitivity is good, but these are difficult bands. So don't expect to map very faint regions over very large areas. It's a complicated. This needs really the best atmospheric conditions. But if you want to map several tens of square arc minutes, that's not an issue. That's not a problem. So that's. But if you want to go to degrees, then that probably becomes a bit. You can only be done for the very brightest regions. So, but it's quite an interesting instrument, and there is no direct complement available in the southern hemisphere. So it's good to make use of that last chance if you have any regions that you think that would be good to observe. Then Concerto is a new instrument since a few periods. It was installed actually beginning of last year, despite the pandemic. And during the pandemic, it was actually installed. It was quite fast that they got it installed. And this actually has a very wide field of view of 20 arc minutes circular diameter. And it has a Martin Puplet interferometer in it. So in the box that you see here, there's actually a mirror that moves at very high frequency at like 8 hertz. It moves in there. That means you get a Fourier transform of the spectrum. And it gives you a low spectral resolution, but over a wide band from 120 to 310 gigahertz. So it was designed to do density mapping imaging of the C2 line in the epoch of reionization and at the end of epoch of reionization. So that actually there's a large program ongoing to do this. But it can also be used for lots of other science. So for example, Sunayv Zeldovic's imaging of galaxy clusters. It's very powerful for this because, of course, you get spectral resolution over the whole band. So you see the minimum and the maximum within the full frequency range. So that is quite powerful if you want to do this. You can do star-forming regions and many other things. One should not use Concerto for high spectral resolution mapping. So it's a bit like sub-millimeter muse or millimeter muse, but not with very high spectral resolution. So one should be keep that a little bit in mind. Yeah. So then some hints on proposals for period 110, given that it is the last time Apex is offered in the ISO time. So you should write your proposals to be self-contained. So don't provide proposals, okay, this is a pilot survey and we will continue in the next periods. Well, that doesn't work, obviously. So those kind of proposals may also not be seen and evaluated very favorably. And so you can write it as a pilot proposal for ALMA, that is all fine, but not for APEX on more ESO observing time, of course. So also don't say it's the beginning of a monitoring campaign or so. So monitoring programs and large programs are not offered at APEX in period 110. So it really needs to be self-contained. Another hint is that I mentioned that Concerto has this C2 intensity mapping experiment. That's all done in the Cosmos field around RAF 10. So that area, this LST range around the Cosmos field is quite heavily oversubscribed. So if at all possible, try to avoid, if you're constructing samples, try to avoid this area from say 6 to 14 hours in RA. Try to avoid it because the pressure there is a lot higher. So I don't want people to spend a lot of time in writing big proposals for hundreds of hours of observing time when we already have the GTO time allocated in this area, which is less of a problem if you have more periods coming, but now it's not so easy. So if you want to use the PI instruments like Concerto and LASMA, you should actually contact the PI team. So I gave the name already for LASMA. For Concerto, it's Guylaine Lagache. The names and the contacts are all written in the call for proposal, of course. So and then to use a bit the contrary of the array area to avoid, then there's the array area between 20 and 24, and between 0 and 4 hours is always less subscribed. So that if you have samples that can go into this area, your chance to get scheduled is a lot higher. So that is a good recommendation, I think, to try to optimize proposals for the available time. So APEX observes almost 24 hours of a day, so it doesn't matter too much in which period you go, but you want to avoid the most oversubscribed. A few other things, you probably want to concentrate on the unique capabilities of APEX, what ALMA cannot do. For example, wide field imaging with the bolometer arrays, Concerto and Artemis is an obvious thing that ALMA cannot do. And then there's these 3 frequency ranges which are covered by the APEX receivers, but not by ALMA. So there's the end of the N-Flash 460 going slightly above 500 gigahertz. That is something ALMA does not offer. And then the 2 edges of the CPS 660 band is also something that ALMA does not offer. So if you have important sources to be done there, also for redshifted targets or redshift 0 special lines, now is the time to do it. And then the other thing that is always useful if you have ALMA observations, you want single dish complements to the ALMA data. So if you have missing flux problems in your ALMA data, so now is the time to do this with APEX, because it can be done easier with APEX than with ALMA. It's often faster because it's only one set of instruments. So the instruments of APEX have been optimized a bit more than the ALMA instruments, which have been optimized for interferometry use. So ALMA offers total power antennas, but it's of course a bit harder to use. And 2 small hints, which also I think Nando may mention, so that the APEX proposal, your APEX proposal will be evaluated by the same people who evaluate your LACIA or Paranal proposal. So they're not experts on APEX necessarily or on submillimeter science. So keep that in mind, that it needs to be very well understood by a non-expert in the field of submillimeter astronomy. And the rules of distributed peer review will also apply for APEX, of course. So I think the limit was 15 hours. Most of the APEX proposals may actually exceed this limit. So it may actually be that a lot of APEX proposals will still go to the regular panel review rather than the distributed peer review. But again, the point above still applies, that it needs to be understandable to non-experts. And all of this may sound a bit apocalyptic, almost, that APEX is no longer be offered, but what will remain is, of course, the data in the archive, and APEX also has quite a bit of data in the phase 3 data release. So I would like to leave this as the last slide to show that there is quite a bit of data already in the ESO phase 3 portal, both imaging of the LABOCA image arrays, but there's also some quite a lot of nearby galaxies. Hundreds of nearby galaxies already have CO2 to 1 observations from the ALSMOG, and the BUS survey very recently that was released. We're also working on having 3D cubes ingested, so that will be the ideal way to look. If you missed your chance this time, that you can still look into the archive if you need to combine Apex data with Alma data. And Alma data eventually will go into this. The aim is that Alma data will also be available from this interface. So that will be your way to find archival Apex data to be used in the future. I'll stop here now.
Thanks a lot, Carlos, for the very nice overview of Apex and also for the hints to the proposal writing. So, are there questions for Carlos? I can start with a comment from Lowell in the chat saying that the deadline is March 25th, not March 24th. So there's one extra day, which is always nice.
Okay, well, nothing stops you from submitting a day before.
I see that Carlo has a hand raised.
So did I understand correctly that the proposals, so the ISO proposal approved through ISO time will only be observed until the end of 2022? So the last months of P110, there will be no observations?
That is correct. And that has always been the case, that Apex has never been observing between January and March. So in that respect, there is no difference between other periods. But we start a bit earlier. So we start actually already the end of August with period 110. And the amount of observing time between the even and the odd periods has always been, we've always been trying to keep that roughly equal. But the main difference is, as I mentioned, DDT proposals, of course, can only be submitted till December.